Hello everyone. Today we are going to study work done by varying force. So let us consider a varying force, or it is also called as a spring force. In last lecture we studied that the work done by a constant force of magnitude F on a point or a object that moves an object by displacement x in the direction of the force is the product, that is W is equal to Fx. The work done is positive if the applied force and displacement are in same direction. But when force varies as it pushes or pulls an object, then work done cannot be simply calculated as product of force into displacement. It is interesting to know that the forces we experienced every day are mostly variable in nature, which is defined as a variable force. A force is said to perform work on a system if there is displacement in the system by application of the force in the direction of the force. In case of variable force, integration is necessary to calculate the work done. So, integration approach can be used to calculate work done by variable force. To find the work done by a varying force, consider a spring. The force acting on any object attached to a horizontal spring, which can be given as F is equal to minus kx, where k is a spring constant and x is displacement of the object attached to spring. From this equation, restoring force or a spring force of a perfectly elastic spring is proportional to its extension or compression, but opposite to the direction of extension or compression. So negative sign is given here. The restoring force or spring force tends to restore the spring to its natural length. Figure shows the position of a spring when compressed and stretched. In compressed position, displacement x is negative, and in case of stretch position, x is positive, that is displacement is positive. We know that spring is an element which is capable to apply force on a body. So let us calculate the work done by a varying force. Consider a horizontal spring of spring constant K, whose one end is fixed to a vertical support or a wall and the other end is tied to a block having mass m. Block is placed on a smooth horizontal surface. For the sake of simplicity, initially x is equal to 0. The position of block is at a position x is equal to 0. At that time, no force is applied, means F is equal to 0. Then we can say that spring is in its natural length. There is no extension and no compression, or it is also called as spring is in a relaxed position. Calculate the work done on the block by the spring force when block moves from position x is equal to 0 to x is equal to x1. By applying a small force on a block so that it displaces by small displacement dx, then the work done is dw. Figure shows the work done by a varying force. Figure A shows the spring is in its natural length, means block is at a position x is equal to 0 and F is also 0. The one end of spring is fixed to a vertical support and the other end is tied to a block of mass m, which is shown in this figure. Then another figure B. Spring is stretched here, means force is applied so that the block moves from point A to A dash by the displacement dx. So dx is the distance between point A dash, A and A dash. And x is equal to x1, means block is at a point B. So distance from A to B is x. So this figure B shows the stretch position of spring. Suppose the block moves from point A to point A dash such that A dash is equal to dx, which is infinitely small displacement. The work done by a force F in moving a block from point A to A dash is dw, which is equal to vector F dot vector dx. So this is the basic relation of work done. As force and displacement are oppositely directed, hence above equation becomes dw is equal to minus kx dx. If the work done in moving a block from position x is equal to 0 to position x is equal to x1 is, therefore the work done from x is equal to 0 to x is equal to x1 is, that means from point A to B, w is equal to integration 0 to x1 dw. Putting value of dw here, so we get w is equal to integration 0 to x1 minus kx dx. As k is spring constant, so we consider or we take integration of x with respect to dx, and which is x square by 2. So w is equal to minus 1/2 kx square 0 to x1. Putting the values of limits, we get w is equal to minus 1/2 k x1 square. This is equation number 1. So in this way, this is a work done in moving a block from point A to point B. Similarly, if block moves from position x is equal to x1 to x is equal to x2. Then work done is W x1 to x2 is equal to minus integration from x1 to x2 kx dx. So we get 1/2 k x1 square minus 1/2 k x2 square. This is equation number 2. If block is brought back to position, means x is equal to x2 to x is equal to x1, that is x2 to x1, means block complete a round trip. So the work done is W x2 to x1 is equal to minus integration x2 to x1 kx dx. By solving this, we get work done x2 to x1 is equal to 1/2 k x2 square minus 1/2 k x1 square. This is equation number 3. To find the work done for a round trip, we add equation 2 and 3. Then we get W x1 to x2 plus W x2 to x1. If we add and solve, then we get which is equal to sum of these two work dones is equal to 0. Hence, from this equation, we can say that the total or net work done by the spring force in a round trip is 0. Thus, total work done by a spring force during the displacement of block from position x1 to x2 and back to x is equal to x1 is equal to 0. Then we consider different cases. Remember 3 positions of spring. First position of spring is natural position or relaxed position, means there is no displacement or x is equal to 0. Second position is stretch position. At that time x is positive. Then compressed position, at that time x is negative. Displacement is negative. Then we consider x1 as an initial stage and x2 as a final stage. So first case is initially, if the spring is in its natural length means no displacement, and for initial stage we consider x1, so x1 is equal to 0, and finally in a stretch position, finally means x2, stretch position, in stretch position displacement is plus x, so x2 is equal to x. Then the work done by the spring force is W is equal to minus integration 0 to x kx dx. By solving this, we get W is equal to minus 1/2 k x square. So this is the work done if spring is in its natural length initially and finally in a stretch position. Then second case, initially if spring is in its natural length means x1 is equal to 0 and finally in a compressed position, that is x2 is equal to minus x. At that time the work done by the spring force is W is equal to minus integration 0 to minus x kx dx, or W is equal to minus 1/2 k x square. Then third case, initially if spring is in a stretch position, that is x1 is equal to x, and finally in a natural position, that is x2 is equal to 0, then the work done is W is equal to minus integration x to 0 kx dx, or W is equal to 1 half k x square. Initially, if spring is in compressed position, means x1 is equal to minus x, and finally in a natural position, means x2 is equal to 0, then work done by the spring force is W is equal to minus integration minus x to 0 kx dx. By solving this, we get W is equal to 1 half k x square. And last case is, initially if spring is in compressed position, then x1 is equal to minus x, and finally in a stretch position, that is x2 is equal to x. At that time, the work done by the spring force is W is equal to minus integration minus x to plus x kx dx, and finally we get W is equal to 0. So in this way, we'll derive the work done by a varying force and its different cases. So we conclude that if spring is compressed, it resists with a force and depends on displacement. If force F is 0, spring is at rest position, displacement x is equal to 0. This is the situation when spring is in its natural length. No load means no force is applied. Then there is no displacement. This is relaxed position of spring, or in other words, we can say that spring is in its natural length. If spring is compressed, then displacement is minus x. At that time, the restoring force or spring force is plus kx, as shown in figure. Spring force is positive, displacement is minus x. This is compressed position of a spring. If force F is equal to 0, then spring is at rest and displacement x is 0. This figure is repeated here because this position will compare with compressed position and stretch position. Again, this position will be compared with stretch position. When spring is stretched, then displacement is plus x and spring force is minus kx, as shown in figure. Fs is negative. Fs means spring force. Displacement is positive. Thank you.